have worked our way through kind of the history of where all this brightness stuff came from, and brightness is really the reflectance of blue light. And then the first iteration of the measurement, the first actual manifestation of it, if you will, in an instrument, you know, started with the General Electric unit, GE brightness, and then it went to Martin Sweet's, Dyno, and Technine, and these names are all synonymous because they all relate to this geometry, and that ultimately became known as the Tappy directional brightness method. And so that was the standard in the marketplace for probably the first 20 years or so, again, going from the early 1930s into the 1950s. And then in the 1950s, the European community said, you know what, there's a lot of things about this brightness measurement we like this piece here. But we're not super fond of this piece that's directional. Remember, we looked at some samples on the directional instrument, and when you rotate it 90 degrees, you can see, in some samples you see maybe a tenth or two. Other samples that are highly directional, you can see as much as a 2/10 shift between machine and cross-machine direction. So it can have a great impact on how are the numbers you get from that if you don't set it up properly. Additionally, if you're measuring a hand sheet, what is the fiber orientation in a hand sheet? Well, there is none. It's random. Fibers could be this way, that way, any orientation in that. So when you're measuring that on a directional instrument and you load the sample on there, depending on where you have that sample located, you can get quite a different set of numbers in that because of that directionality of the light source and the non-directionality in this hand sheet. So the European community said, you know what, we want to take some of these things and we want to then move them over to a new standard that's going to take advantage of what we see as the good with that tapping method and improve on it in their eyes. And so what they did is they began to research and say, okay, if we were going to make a measurement, let's do it with this same blue filter concept that's in the original design, but instead of using a directional, let's do something that's going to try to take out the directionality in the measurement. And the best way to do that is to use a sphere, if you will. And if the sphere is coated with a matte high reflectance coating, white coating I should say, you can take and you can shine light into that sphere. That light's going to reflect off the sphere walls internally, and if we do it right, it will be of equal energy so that when a sample sits there, it can be illuminated by light coming from all angles. And as a result of that, you won't get any directionality. So after some work, they came up with this concept of this sphere. Okay, so this sphere is roughly 150 millimeters or 6 inches in diameter. Okay, and as you can see, it's got a high reflectance matte white coating in there. Okay, you've got the sample port sets here. The photocell sets here. The sample port is here, so you load your sample with that. You either have one or two openings for your light source in that. So the goal is that you would shine light into this. Light would reflect off the sphere walls, and then equal energy would then strike the sample here. So what we have then, if we draw that up here, is we've got this sphere. That's round, not like that. Okay, and you have a photocell that sits at the top of the sphere, capturing light, and then directly below it at that perpendicular location, you've got an opening here, and this is where the sample sits. Okay, so you've got this setting at this, so this angle represents 0 degree. So you have 0 degree viewing here, just like you did here. So you're looking directly at the sample, but the difference comes in how it's illuminated. In the tappy or directional, it's got a single light source illuminating from 45 degrees. This now has a light source sitting over here. Again, it could be one or two light sources. There could be another one here. But we're going to take this light. If you look inside one of the spheres, you'll see a little paddle in there. And again, that's coated with the same coating that's that. And what that paddle is for is that no light can come directly from the lamp and strike the sample. it sets right here to deflect that energy back into the sphere. So now the light comes into the sphere, it's bouncing off the wall, so that takes that energy and then scatters it all around that sphere, so that what light strikes the sample here is diffuse. It's light coming from all angles with equal energy. Now, can we guarantee you that it's equal energy from all angles? No, because it's not going to be perfect, but it's pretty good. It's pretty good. So the goal here is that you are going to put light into the sphere, light's going to reflect off the sphere wall, scatter about, and then it's going to illuminate from all angles. So with that being the definition, what that is, this is called diffuse, because that's the illumination, 0-degree viewing. Diffuse versus directional. Okay, so the two methods illuminate the sample differently. How they measure it then, once that light goes off to the photocell, they're identical. The filtering of the two instruments, whether it's TAPI or ISO, are the same, doing the same filter function, but how they go about collecting that light is different because they illuminate energy differently with that. If I take any sample and I hold it in my hands and I rotate that sample, as I rotate it, I view that sample differently because light is striking it differently and my eyes are responding to that differently. It's the same way with this. It's a different geometry, therefore it's going to create a little different look, and it's going to create a different number potentially from that. So, the ISO, or the European community, went about designing this and saying, we think this is an improvement over that because it eliminates the directionality. There are plenty argue still today that this is a better geometry than that because it has the directionality aspect of it. So it's one of those 50-50 things that are out there. But nonetheless, this method was developed in the 50s and ultimately became an ISO standard. There's 2469 and 2470 that define what that standard is. And again, it defines the geometry of the sphere. It defines the filter function of this, again, which is a match to this one over here. And it became an instrument. Much like the Institute didn't make instruments, the group in Europe that designed this did not make instruments. And so they went to, in the 1950s, the Carl Zeiss company. And Zeiss is, we still know them today as one of the leading optical experts. They do some really good work in the area of filtering and lensing and things like that. And they went to the Carl Zeiss company and said, hey, would you guys be interested in making this first instrument? And so they did. And so this is one of those early on instruments, just like the TAPI instrument that had the knobs and adjustments on it. You could adjust this and you would read the gauge here. So it was very similar to that early TAPI brightness instrument and how basic function it was in that. But it was really the first instrument that came to market. The other piece that came from that was a name. Okay, so you often hear a phrase called the Zeiss Elrepho. And that's E-L-R-E-P-H-O, Elrepho, which is in itself a little bit of a different name, but it has a meaning. It is electro-recording photometer. And so you came up with this name, and you hear that name in the marketplace today, just like you hear GE brightness, you hear Elrepho brightness. Well, Elrepho was the original name of the first instrument. But like the GE line, where eventually it went to, from calling it GE to a Martin Sweets, to Louisville Lunchbox, to Diano, to Technonine. Now you hear Directional, you hear GE, you hear TAPI, you hear Technonine, you hear S4 brightness, you hear Test Plus brightness. You hear all those things. They're all the same thing because they're all the same directional geometry. Well, it's the same way over here with the European community. You hear the name Elrepho as kind of that generic name meaning Elrepho or diffuse. But today there are a number of instruments that do that same measurement, including some of the ones that Technonine makes, that do this diffuse ISO brightness, so the diffuse illumination 0-degree viewing. So you might hear today Elrepho. One of our original instruments was a TB1 or micro TB1C. That one also did color. Today you'll hear color touch because that's another instrument that we have that does the same measurement with addition to color. So ultimately what came from it is that now you had these two methods. You had the TAPI method, which came first, which took advantage, came up and kind of generated this whole concept of the blue reflectance, and that was originally on the market, but because of some of the issues with directionality, there was a group that wanted to take the basic concept of the measurement and improve on it, and they did that through what they use with the sphere. So today these two methods still exist, and what's important is that when you're measuring one of these, you communicate, is it TAPI, is it ISO, is it directional, is it diffuse, is it GE, is it Elrepho? We use the same word generically in brightness, but how we go about getting those measurements, how we go about taking those measurements, how we go about collecting that light, how we go about illuminating that sample is different from instrument to instrument. So those are the two methods that we have in the industry today, TAPI and ISO. Two very distinct standards which are written that make it for us as manufacturers and you as users of the equipment to know exactly what it is that you're measuring. The next video is about, all right, now whether we have these two methods, how are they similar? What kind of data can I get from one and what can I expect to get from the other? So tune into the next video and we'll talk about the differences and the similarities between the two test methods. Thanks.